So for this practice problem, it's going to take us back to everything that we've done in the previous unit, because the first step is to find the electric field of two charges, and the distance x is L. So what we have to keep in mind, and I'm just going to erase that and replace this with L. What we have to keep in mind is that the electric field equation is equal to K integral dq over r squared. There's only one charge, and we integrate for the full charge. But in this scenario, each of these charges are point charges. So what we're going to do is treat this as a point charge, kq over r squared. And there's two of them, so we're going to do 2kq over r squared. But remember, with electric field, direction does matter. So before we get into this, you always start by drawing out the electric field. So it goes out of the positive in this direction and out of the positive in this direction. If I were to think of this as theta, which translates to that right there, the x component, which is the net electric field here, because the y components cancel, is cosine of theta. So in this scenario, we would need to figure out what r is, which is this, and we would also have to figure out what cosine theta is. What I've seen is students do this two different ways. You could use one, the similar triangle rule, or you could notice the fact that since L, one side is L and the other side is L, it's a 45 degree angle here. So you could either take cosine of 45, or you could say cosine theta is equal to adjacent over hypotenuse. First, we have to figure out what r is. It's the square root of L squared plus L squared, which is the square root of 2L. And then for cosine theta, if I wanted to use similar triangles, I would get L over root 2L. And so cosine theta is 1 over root 2. You'll notice that we get the same answer, so I'm going to use both methods. I'm going to take the electric field is equal to 2kq. My r squared is 2l squared, because it's root 2l quantity squared. And then my cosine of 45, which I don't know off the top of my head, I think it's root 2 over 2. Let me just quickly check my equation sheet. Yep, cosine 45 is root 2 over 2. So I can simplify that. These two cancel, and I get root 2kq over 2l squared. In the answer key, it'll simplify this down to kq over root 2l squared, which is the same thing. If you were to substitute cosine theta as 1 over root 2, you'll see that you get the exact same answer. For part B, this one should be a pretty easy equation, and this is something that I want you to be able to think of very quickly. Force is electric field with 2 q's instead of 1 q. So if I take the electric field and multiply it by a test charge little q, then I would get, and I messed up my q's here, I'm going to use blue. When I substitute q in, it should have been a capital Q, because both of these are capital Q's. When I plug in my test charge, it's supposed to be a little q, because that's this little q at this point right here. So to simplify this out, I just write out my K big Q over root 2 L squared times little q, and that is my electric force. Now part C is asking for the electric potential at distance x is equal to L. So I'm going to use the same similar equation, except it's the K times the integral of dq over r instead of r squared. And I want you to keep in mind that there is no direction for potential, and because they are point charges, I can just represent it as K big Q over r, and there are two of them. The only thing is I have to rewrite my r in terms of variables that are given, and so it's 2kq over the square root of x squared, the square root of 2 over L, okay? So the next part D, it's asking us to determine the electric potential energy, so U, and in this scenario, we, just like how we thought of force, electric potential energy has two Q's versus voltage, which is the same equation, or potential, which is the same equation with one Q. So I can just take my potential equation and multiply it by the test charge, which is 2kq little q over root 2L. Okay, now the last part is asking for work. And one thing I want you to think about carefully is that it's asking for the work done by the external force. And remember, we are taking a positive charge and moving it from infinity to a position on the x-axis. By moving it from infinity in, then we are increasing the potential. When we think about the work done by the external force to move that object, it is going to be what we got for the final potential. It's 2kq, big Q, times little q over root 2L. Now, this question isn't on this problem, but if I asked you for the work done by the conservative force, that's the work done by the electric field and the electrostatic force, that would give me the same magnitude as the external work done, except it's going to be negative. And that's because the electric field is trying to push that positive charge away, but that positive charge is moving in the opposite direction than the electric field wants it to, so it is considered negative work.